All right, let's take a look at today's lesson. So what we're going to be doing today is looking at derivatives in context, trying to determine what do they mean? How are we going to describe them? That's kind of the overview of today's lesson. It's mostly about conceptual. We are going to do some approximation of derivatives, but the first part is just entirely conceptual. The way that we write our reasons is pretty important. We're looking for, when they ask us to interpret in context of the problem, we're really looking to include three different things. Now, I have had some teacher friends that would put pictures of nuts on the ceiling. Noun, unit, time is basically what we're looking at. So, all right, so what we're looking at is to include, and I'm just going to write this up here, to make sure to fully describe what the scenario is, we need to be sure to list a noun. So the acronym that some teachers use is N, U, and T. So it's a noun, unit, and time. Those are the three pieces of information that we need to be sure we include whenever we are describing or explaining something in context. Okay, we need to be sure to use the noun, the unit, and the time, and we get that information from the text, from our prompt. So I have a couple of examples of that, kind of explaining things in context. How would you word this? So let's look at our first scenario where Mr. Sullivan wants Mr. Bruss to finish creating his packets in Algebra 2. The number of packets he has completed is modeled by, and here's our function P of T. So let's make a note that this is a position. And what does it do? It's the number of packets in weeks. That's basic number of packets completed in weeks. That's what that stands for. So we got to kind of get our minds wrapped around that. So P is the number of packets, W is the weeks. So if this value right here, this is a position value. P of 10 equals 1. So let's kind of pick that apart and see what those, what all that stands for. This is weeks, right? That's how many weeks. And this is number of packets. So that's what those things are. So now let's put it in a sentence. We need a sentence that has the noun, the unit, and the time. Okay, so what we would say. So I would say, at week 10, and that gives me my time. At week 10, Mr. Brust, and I love for you to say back the words that they have said, in the prompt. You're actually saying things from the prompt. At week 10, Mr. Brust completed one packet in Algebra 2. So let's kind of underline. So we've got our time. So that's time. I'll just use that color to underline time. We've got our unit, which this is a packet is the unit. And we've got our noun, which is he completed. He completed one packet in Algebra 2. And we can add this to our noun. So we've got all three things are mentioned, so we are good to go. So I want to pause there for a second. Are we okay? Mr. Brust completed is like is the subject, if you will, and they call it noun, but it's really like the subject of the whatever the context of the problem is, that he's completed one packet in Algebra 2. So now we're kind of shifting gears and we're looking at P prime. So P prime is the first derivative. So let's just make ourselves a little note. So this is not the position. This is the first derivative. And the first derivative, or well, derivatives describe rates. So this first derivative, or this is a rate. Okay, so we need to think about this in terms of rate. It's the rate that the packets are being completed. The rate the packets are being completed. That's what this first derivative would describe. So now let's pick that apart and let's figure out what this means in context. So I like to write the time first. It doesn't matter. Really, it doesn't matter the order you write the words in. As long as you get them all in and they make sense, then it's fine. It doesn't have to look exactly like mine. So the 39 is talking about the 39th week, right? That's a week. So let's say at 39 weeks, the rate the packets are completed is 4 packets per week. Okay, so let's underline. So here is my time at 39 weeks. So that's my time. My units are packets per week. Like up here, my unit was packet. This is packets per week. Those are my units. And my noun, or what the action that's going on, which I guess isn't a noun, is it? It's the subject, I guess you would say. Instead of a noun, I think they say noun because that's it makes a nice little acronym, right? NUT, N-U-T, noun, unit, time. It's basically the subject. So it's the rate, the subject, the rate the packets are being completed. That would be like the noun. The rate the packets are completed is 4 packets per week. So I have my noun, the rate the packets are completed, or the action. Maybe a better word would be what action has happened. The action, the units, and the time. Okay, are we okay with our very first problem in context? Okay, let's look at another scenario. So in this first scenario, we're given the position, and then we're given, we have to explain the position in context, and then we have the first derivative, explain that in context. That was our first problem. The second problem, we're actually not given a position. The second problem, let's read through it. The rate at which Mr. Kelly is buying baseball cards per year is modeled by B of T. The rate at which he's buying baseball cards per year is modeled by B of T. That means that is a first derivative. That's a rate, right? That is not a position. That's not the number of cards he's buying. It's the rate that he's buying. So we need to really make ourselves a note to make so that we don't, get it confused. This is a rate. This is a rate. So we're going to say this is like the first derivative. This is not a position value. So our units, T is measured in years, and B stands for baseball cards. Okay, so now when we interpret this, and I hope you can see how vastly different the interpretation would be depending on which type of equation you're trying to interpret. So here we've got this is actually not a position, but it's a rate. That is a rate. The 3 stands for time, right? And then in this case, it's years. And the 150 stands for rate he is buying baseball cards. Okay, so that's what those are. So we need to identify what do those numbers mean. Okay, so the 3 is the time, which is in years, and the 150 is the rate he's buying baseball cards. So let's try to interpret, what does this mean? B of 3 equals 150. So it would mean the rate Mr. Kelly is buying baseball cards at year 3 is 150 cards. So a rate is cards per year, or a first derivative would be like the item per the time, right? Cards per year, meters per second, you know, whatever scenario we're dealing with. So let's see that we've got all of our parts here. So we've got our time. Our time is year 3. Okay, we've got our rate. Our rate is cards per year. And our noun, or the action that's happening, is that the rate Mr. Kelly is buying baseball cards. That's kind of the action, or you could, I guess, view it as the noun. The rate, and notice this we need to write this here. The rate that Mr. Kelly is buying baseball cards at year 3 is 150 cards per year. Okay, so questions on that? Okay, so then that makes the second part just, I think, really kind of weird, doesn't it? We've got a derivative right here. This is B prime. Well, we already had a rate. B was already a rate. So if we're going to put it in terms of equations that we're, probably familiar with, this would be related to the second derivative. The second derivative, that's what this would be talking about, the second derivative. The second derivative is the rate the first derivative is changing. So we might want to just make ourselves a note. So this is, second derivative is the rate the first derivative is changing. That's what the second derivative is. It's the rate of the first derivative. Okay, it's the rate that the first derivative is changing. Okay, so let's try to piece together what in the world they are talking about. So the 4 is in years, and the 10 is something to do with the baseball cards, right? It's the rate that the rate is changing. Okay, so let's see how we could write that. All right, so this one is I think it's actually more, this second one, I think is more confusing than the first one. Starting out with a rate, and then with the first derivative, and then with the second derivative, I think that takes a little bit more, I don't know, it's more intense, I suppose. So let's kind of put our mind around how would we describe this. So I'm just going to put at year 4, I've got my time. The change in the rate that Mr. Kelly is buying baseball cards is 10 cards per year. This is a second derivative, so It's the units that are, or you could write it as 10 cards per year squared. That's also acceptable. Which sounds really weird, I know. So let's go through the NUT, the noun unit. So here's my time. Time is year 4. My units are a little strange. This is like the second derivative units. So what you would have is an item per time per time. So in this case, the item is cards. It could be meters, but it's cards. Cards per year, or again, you could write it like that, cards per year squared. That's our unit. The noun or action that's going on is, and we need to see, remember how up here we wrote the rate? So here we're writing the change in the rate. The change in the rate. Okay, the change in the rate really describes to us what's happening to the rate. It's the rate, the first derivative is changing. The change in the rate that Mr. Kelly is buying baseball cards is 10 cards per year. Now, I really encourage you to write change in the rate instead of the rate is increasing or decreasing. It just makes your life easier. If you write the change in the rate, then you're just going to write the number you got, whether it was a positive or negative. An example, so I'm just going to tell you why. So here's an example. If let's just go back to our first derivative, I think that's easier. If f prime of x, let's say is negative 5, okay, and let's say wherever f prime of 2 is negative 5, okay, then if I say f, so I don't know what f is, just come up with something. What could that be measuring? Temperature? Let's just say this is f is temperature. Okay, so let's just say F stands for temperature. So this means the temperature is changing at, let's just say that's weeks, I don't know. The temperature is changing -5, I don't know, degrees per week. Okay, if I said that temperature is decreasing at -5 degrees per week, would that be okay? That is not okay. Saying decreasing and a negative rate, that's kind of like a double negative in English. Don't they get mad at you for that? Mm-hmm. Like not, or I don't know, no double negatives. So that's why it would be beneficial if you use the word change instead of increasing or decreasing. I'm just saying it will make your life easier. Because if you say here that the temperature at week 2 is decreasing at -5 degrees per week, that would be incorrect, right? You can't decrease at a negative. That's not okay. That's like a double negative right there. So this is a case for why it would be a really good idea to just use the word change instead of increase, decrease. Does that make sense? I don't want that to catch you. Okay. So that's a lot of the words. We're going to continue with words on this next example. And this is still trying to get really a good knowledge and understanding of what is the first derivative doing. What does it do? So my question here, to know if something is increasing or decreasing, and this something, we don't know what it is. Let's just call it it. And just let me say, using it really almost makes me like break out. I don't know. This is terrible. You don't use the word it like ever. But that's so, what is the something? I don't even know. But to know if something is increasing or decreasing, what you want to do is you want to check the sign of its derivative. So if it is temperature, you would check the sign of the temperature's derivative. If it is, I don't know, cards, you would want to check the sign of the cards, or buying cards, or whatever that scenario was. So that's what you would do. You would check the sign of the derivative. And do we recall, have we talked about that before? Increase, decrease. So if the derivative is less than 0, then what's happening? Then f is decreasing. If the first derivative is greater than 0, then f is increasing. So that's what the first derivative does for us. It tells us how the position is behaving. It's a clue for us. Like, if we know that the first derivative is positive, then we know that its position, or f, is increasing. Increasing, in other words, the graph is going up. If we know the first derivative is negative, then we know its position, or f, is decreasing, or the graph is going down. So that's really important information for us. That makes finding derivatives quite useful. It helps us determine information on the position. So let's look at these scenarios. If height is increasing, or height is increasing if h prime would be what? Positive or negative? Positive, or h prime is greater than 0. That's what we would see. Height is increasing if h prime is positive. Velocity is decreasing if the derivative of velocity is negative. And the derivative of velocity, what is the derivative of velocity? It's acceleration, right? So, or you could say acceleration is less than 0. You could use either of these, either the derivative of velocity is negative or acceleration is negative, to show that velocity is decreasing. Now we're looking at just random things. Mr. Brust's IQ is increasing if, and I'm just going to write that equation as IQ. The derivative of IQ is greater than 0, which we don't know. I mean, we don't have that equation, but there could be an equation written for that. And a smile is decreasing if the derivative of the smile is less than 0. So what these examples are trying to demonstrate is it's whatever the thing is that you're measuring, whatever, I don't know, IQ, smiling, velocity, height, temperature, all those kind of things. That's how you're going to be able to make some sense of that. Okay? All right, so let's look at number 3, more about describing things in context. All right, so if F is the bunny population, so I really highly encourage you when you're reading through these words to make yourself notes. Please don't just kind of breeze over the words and keep going, because that really will not help you. You need to dig into the words. F is the bunny population. What does that mean? Does that mean, is this a position or is it a derivative? It's a position. It's bunny population. So this is a position. Okay, it's the bunny population after X years. So X is in years. Okay, great. So if F is the bunny population after X years, then what would F prime be? What would the derivative of bunny population tell us? It's the rate. It's the rate. What? The rate the bunny population is changing. You with me? So it's the rate the bunny population is changing. That's like my noun. So I need, or action, if you want noun or action. I also need what? I need rate. I mean, like a unit and time, units and time. So it would be changing in what? The bunny population. It'd be changing in population per year. You got it. Population per year. Whatever the population is, 20, 20 bunnies per year, or whatever that number is. That's a number. The population would be in like a number, right? Like 50 per 1 year or whatever. Okay. The next one is if, now we're changing gears here, if F is the rate at which the bunny population increases. Okay, so F is no longer a position, is it? It's no longer a position. This is going to be like a first derivative. This is a rate. If F is the rate that the bunny population is, and they're saying it's increasing, then what would F prime be? F prime would be like a second derivative, wouldn't it? Yeah, it would be like a second derivative. F prime would be like a second derivative. So let's put that in words. So the F prime would be the change in the rate that the bunny population is increasing. And we need our units, right? So it would be what? It would be the change in rate that the bunny population is increasing. Yep, you got it. And population, which whatever number that is, population per year, which again, you can write as per year squared if you prefer. Okay, are we getting a little comfortable with the wording? We can do that? Okay, great. So the last example is actually one that has like calculations. So we are using the data in the table on the left, and we're supposed to answer these questions. They want us to estimate P prime of 15, and we've done this kind of thing before. Y'all remember that? P prime of 15. Do you remember where do I go on this table? 15 would fall right in here, wouldn't it? 15 would fall in there. So if I want to estimate the rate of change, do you remember which formula I use? You got it. I would do like, and I'm going to write it in abstract form, and then we're going to put the numbers in it. But again, you don't have to write the abstract form. So we're going to do will be P of 20 minus P of 10 over 20 minus 10. So which, again, you don't have to write that part, but you do have to write the actual number part. The numbers would be 150 minus 120 over 20 minus 10. And what is that? That's what, 30 over 10. So then this would be 3, and my units would be, here's how I find them. I'll just look right here, people per year. I take my units right off of what those variables mean. There should never be like a question on what the unit should be. You just take it off of the variables. So 3 people per year. Okay. The last one is estimating P prime of 20. What did we do before? Do we recall? I mean, what I would do, my recommendation is to go to either side. That's my recommendation, is to go to either side and do those. They would probably take it if you did either this side or this side, but I don't know, it seems more even to do on either side. So that's what I would do. So writing it in abstract, we would say P of 30 minus P of 10 over 30 minus 10, or again, that part's optional, but you have to write the numbers. So 200 minus 120 over 30 minus 10. And might I also add, do not do that, write it down first. Like, don't do 30 minus 10 in your head and put 20. Just, we need to see the fraction and the subtractions. We need to see that. So now you can go ahead and do that part. So what is that, 80 over 20? Or what does that do, 4? So 4 people per year. All right.